math. We are going to do this quite fast, just so we can get done with everything that we need to get done. But we've come to the last section, really, in chapter 3 that we're going to talk about, which is rational functions. And we really want to get to this. You want to see an equation, you want to be able to graph it. That's kind of what you want to get to. I'm going to be writing down a whole bunch of steps, but you should be able to, again, look at an equation. You should get details from that. The only thing that maybe you might have to actually do some work on is the x-intercepts. The rest you should be able to really graph a rational function right away. Okay, and the other one probably is oblique asymptotes, those guys right here. So we've got some vocabulary to learn, but we'll finally get to the last section where we want to graph these. Okay, but quickly define a rational function. What is that? It is really a ratio of two polynomials. So you got a polynomial on top, you got a polynomial on the bottom. And remember, with rational functions here, you can't have zeros on the bottom of a fraction. So this d polynomial, this rational function is defined for everywhere except when d is equal to 0. So let's talk about domain first before we get to other places here. So this is from the example from the textbook here. We got 3x squared minus 12 over x minus 1. And again, just kind of thinking with me here for a little bit. We don't care what happens at the top, it's the bottom that's the issue. So it's whenever this is equal to 0. So what we do is we set it up as, when does x minus 1, we can say equals 0, doesn't equal 0, add 1 to both sides, there's my answer. So this function works except for when x equals 1. It does not work here. Alright, and the way we write it in interval notation is, again, negative infinity to 1, union, and then 1 to infinity, parentheses around the 1, because we are not including that as our domain. What happens here is we have to factor. For b, we would have to factor this down. And once you factor down, set it equal to 0, solve it, and now you got two different places. You got to be careful here, because if you add the 4 here and the 2 here, you've got to still think about, along the number line, who am I going to hit first? Am I going to hit the 2 or the 4 first? You're going to hit the 2, so if you go from negative infinity, you're going to go up to 2, the union, 2 to 4, union 4. And the next one, which is c, this one here, again, notice these two will actually factor, right? X squared minus 4 doesn't factor into x plus 2x minus 2, but we're not doing that right now. We'll do that a little bit later for something else. We just care about what happens right here. And the problem here is that there is a 2 is the issue here. X can't equal to 2, so again, interval notation. Alright, practice problem for you. All yours. Give you guys a minute. guys got it here? So again, it's this right here set equal to 0 in factored form. It gives me these two. It's a -5 and a 1 set equal to 0 each of those. And we're solving for x equals 5, x equals -1. And again, along the number line, where do you think you're going to get to first? It's going to be the -1 we're going to get to. Then it's okay from -1 to 5, not including those. And then it's okay from 5 on. So we're good there. You don't need to graph it here, but I wanted to at least graph it to show you what it sort of looks like, what's the problem areas here. And if you go out to 5 and you go out to -1, at x equals 5, there it is. This is called the vertical asymptotes. That's the problem here, because there's a break in a graph. There's never a time this can equal 5. Also at -1, there's a vertical asymptote here. So the domain is going to really restrict it by a vertical asymptote or something called a hole, and we'll talk about that when we get there. Okay, the graph of these here, since we're graphing it anyways here, don't we also have an x-intercept at 3? If we set this guy equal to 3, so the graph sort of looks like this. And again, we'll figure out why that is so in just a little bit here. There's your graph of these guys. So our main job is really by the end of this section, you look at this and you graph this. That's kind of what we want to do in the next hour. Okay, there's two different ways to graph these. Remember how we did transformations? We can move to the left, to the right, expand it out, and all that good stuff. Some textbooks do teach that as a way to solve this. So I'm going to go through it. This is not the way the book teaches it, but I want to at least show you just real quickly here, just to see how it is. But the whole concept of vertical isotopes, the A being the vertical isotope, what we talked about there. So you got this one. This is exercise or practice problem number 2. Again, maybe don't even write this down, just kind of think with me, look at it, see if this makes sense. Technically there's a multiplier of 3. So what we do is we take the 3, put it out in front, and you have this. Isn't this something called the reciprocal function, is that right? 1 over x. You guys all remember 1 over x? It does a little loop, something like this. Let's see if, like this. There it is. There's called the reciprocal function. What does this little -2 is going to do? Since it's inside the function, it's going to shift to the right 2 units. If it was a -2 out the outside, it would have shifted it down. We good? Since inside the function, it shifts left and right. Because of the 3 on the outside, vertical stretch of 3. We good? So you kind of see how that all happens here. So vertical stretch, we got a 3. We have a right shift 2 units. So that means this vertical line has shifted over, and the horizontal line has not, because we didn't go up or down. With that then, instead of going 1 over, 1 up, kind of like this one, we go 1 over to the right, then 1 up to the top. Now we go 1 over from the middle, and we go 3 up. Again, 1 to the left, 1 down normally. Now it's going to be 1 to the left, 3 down. And then you can fill in a few more dots here, but you can kind of see how that's going to go. So it's really a shifting of the reciprocal function. Okay, a little bit more tough. How about this one here? This is another example here. Oh, real quick here. Sorry, I've got one little problem here. Notice you have a binomial here. If you're going to do this by transformations, you're going to have to divide one into the other and see what happens here. So again, that's going to be a 2. 2 times 1 is 2. Subtract that, you get a 3. So there's what I'm going to graph. I'm going to graph this. So I'm going to do a little bit of work there. Okay, let's do that again. Let's put that 1 on front, put the 2 in the back. Take the 3 out, put it in front, and now we're ready for graphing. We good? See what's going to happen. The little plus 1's going to go where? Shifts it over to the left, the 2 here, up 2, and a vertical stretch of 3. Cool. Okay, again, vertical stretch 3, vertical shift 2 up, and a horizontal shift left by 1. So again, that affects the vertical asymptotes and the horizontal asymptotes. So since we went up, we have a horizontal asymptote, that's what this is, has shifted up. The vertical asymptote have shifted over to the left, and then again that little vertical stretch up of 3, down of 3, fill in a few more dots, and you got yourself a graph. The problem with this one is sometimes, remember like the previous graph that I showed you, sometimes you got 2 vertical asymptotes. Then you're really confused at that point. So we normally don't deal with this one here, because this one normally just deals with one single vertical asymptote. So we're going to do a more generalized approach to it. Okay, so vertical asymptotes come in 4 different ways. You could have a vertical asymptote that actually goes up like this. So what happens here is that you have x minus a, and you have it to a squared power, or in some kind of even power. If it's going down this way, somehow you have a negative over here, and you have a x minus a squared. Good there. So even powers, 6th, 4th, 8th, 10th, will give the asymptotes, and the graph is going towards the same direction as it gets there. And again, all in your textbook here. What gives it a split direction? Any kind of odd power. So 1 over x minus a, that would give you a split direction. Or 1 over x minus a to the 3rd power, something like this. You know how we talked about multiplicity? Remember that with polynomials? Again, sort of something like that. We don't call it multiplicity, we call it direction. So either same direction or split direction. This gives you a split direction. And again, somehow x minus a or x minus a cubed, or to the 5th, or to the 7th, or to the 9th, any kind of odd power. Question? Yeah, there's a horizontal shift that happened in this one. It shifted up as well, where this one doesn't have a horizontal shift. Good there. So there's a reflection, and then there was a horizontal shift up 5 units. That's kind of what happened. So yeah, there was a reflection, and then a shift. Yeah, it's abstract. It's more just talking about the vertical asymptote, or just kind of concentrating on that piece there. So same direction or split direction, you have 2 different choices for vertical asymptotes. Okay, now let's find the vertical asymptotes. How do we locate the vertical asymptotes? Alright, and the important word here is, from your textbook, is they do not have a common factor. So whenever you're looking at the vertical asymptote, you're looking for the problem area whenever you already have, when it's already in factored form and its simplest form. So let's talk about some examples here. We'll look at it. So 1 over x minus 1. Where is our vertical asymptote? It's when the denominator equals 0. Again, very similar to domain, right? Because domain is, it breaks the domain there. For b, you have to split this off. So how many vertical asymptotes do I have? 2. One is at x equals 3. One is at x equals negative 3. Got 2 of them there now this time. Okay, the next one. X squared plus 1, when does that equal 0? It never is is equals to 0. There's never a time where there's a vertical asymptote on this particular problem here. That's kind of interesting how that's going to work. So hence no vertical asymptotes for this one. Okay, our problem. Find me the vertical asymptote, or asymptotes, if there are multiple ones. Alright, what we always have to do is we have to put it to factored form just to see if, possibly, the number on top is going to cancel with a factor on the bottom. So x plus 1 does not factor, but the bottom does. Factors into x plus 5x minus 2. And notice that nothing cancels, nothing reduces. So then I have two vertical asymptotes. So there is no common factors, any one here. At that point, I got vertical asymptotes. Two of them, one is x is equal to negative 5. The other one is x equals to 2. Cool. Let's get a little more complicated though. What happens here? How about if you have an x squared minus 9 on top, x minus 3 on the bottom? So if you write this in factored form, what's going to happen is the x minus 3's cancel. So real quickly here, kind of weird. This is x does not equal 3, still part of our domain. There's still a domain issue here. But the graph that we're going to graph is x plus 3. So if things do factor and they cancel, we still have to account for this right here. And so what we do is we account it by saying that there's a gap or there's a hole in our graph. I think everybody can graph this, y equals x plus 3. When we graph it, there it is, except right when x is equal to 3, there's a little hole or a gap in the graph. That's sort of the difference between this and that. Cool there? One has a hole, one doesn't. It's kind of one has a gap and one doesn't. But there are no vertical asymptotes there on this one. Okay, for part B, sort of same thing happens. X plus 2 is on top, x squared minus 4 is on the bottom. Again, this is in your textbook here. The bottom factors. X plus 2 cancel. As far as domain is concerned, x cannot equal a negative 2. So in this case, what we do is we have a vertical asymptote, and we also have a hole because of our domain restriction here. I got a vertical asymptote at, I got a hole at negative 2, and then I have a vertical asymptote at x equals 2. So how does the graph of that look like? There's my x equals 2 vertical asymptote. There's my x equals negative 2 gap or hole. Cool. So a domain restriction could either produce a vertical asymptote or a hole, depending on what it needs to do. Okay, our practice problem, all yours there. Try it yourself. factoring is a little tiny bit more difficult. I'll let you guys ponder what 3 minus x is going to do. Alright, so remember from algebra rules here, I don't like to have the 3 in front and the x in the back. I like to turn it around so that the x is first. In order to do that, I have to factor out an x, or I factor out a negative there. And then that's the difference of 2 squares, so that'd be x plus 3x minus 3. So if I'm just looking for vertical isotopes, that's it. If the question is find me all the vertical isotopes in factored form and simplest form, that's what I have. And so that means I have a vertical isotope at x is equal to negative 3. We good? So for homework purposes, that's what you would write. You just write vertical isotope x equals negative 3 and you stop there. Forget about the whole whatsoever. I want to show you the graph of it on a calculator, because that's the little problem here. At x equals negative 3, there's my vertical isotope right here. The only problem is your calculator does not account for the whole. So if you're to graph it on a calculator, you have to understand that x equals positive 3. There's a little hole right here that you have to account for and draw in if you're to say, okay, draw this graph for me. Cool? So calculator's not going to deal with it. Okay, so vertical isotopes, one aspect of it. Let's go on. Next is something called a horizontal isotope. And these little things right here, let's talk about it here. It says f of x goes to k as x gets bigger or x gets smaller. So really what's happening, the question for a horizontal isotope is what happens at the ends. Horizontal isotope is saying, okay, if x is really, really huge or x is really, really small, where's the graph very, very close to? That's kind of what's happening here. You can never cross a vertical isotope, but you can cross a horizontal isotope. So kind of careful there. We'll see some that do cross. Okay, but let's get to locating them. How do we locate them? In your textbook, you have this. You have n of x divided by d of x, and then remember this is the abstract way of writing a polynomial. So there's 3 different cases here. So first of all, we've got to think about this here. The degree of the numerator. The degree of the numerator is n, and the degree of the denominator is m. So it all depends on the degree. And there's 3 different cases. There they are. If n is less than m, then we do have a horizontal isotope. The horizontal isotope is the x-axis, and the equation for it is y is equal to 0. I'll give quick examples for each one. So let's say we're graphing this. Y is equal to 1 over x. What's the degree on top? 0. Degree on the bottom? 1, right? So degree on top is 0. Degree on the bottom is 1 because it's x to the 1 power. So notice that n is less than m. Now if that's the case, my horizontal isotope is y equals 0. Or a little different example here. How about this one here? Is 3x to the 5th plus 7x minus 4. And we have for myself 4x to the 6th on top, 5 degree on the bottom, 6. Eventually, when this graph gets higher and higher or lower numbers here, eventually the graph is going to be up here. Now we don't know whether it's a little bit above the x-axis or a little bit below the x-axis. We'll figure it out a little later. But it's tending more towards 0 as it gets higher numbers for x or lower number for x. It's somewhere over here. It's slightly above the x-axis, slightly below the x-axis. Okay, what happens if these guys are tied? What happens if I have, let me rewrite the last one here, 3x to the 5th plus 7x minus 4, and I have a 4x to the 5th plus 10x minus x squared. If they're tied, the horizontal asymptote is the ratio of the highest, or the leading term, coefficient of the leading term. So it's the ratio of the coefficients of the leading term. So in this case, I do have a horizontal asymptote, and it is 3/4. Alright, the other way, what happens if the degree on top is higher than the degree on the bottom? So 3x to the 6th plus 7x minus 4, 4x to the 5th plus 10x. Let's change it up a little bit here. At this point, you have no horizontal asymptotes whatsoever. It's not going to ever lend itself close to a horizontal asymptote. Bless you. Cool. Alright, let's go for it. Let's quickly find some and then we'll practice as well. You know what? Actually, I'm going to jump to this one right here. I think each one of them would be good. So all yours here, this is practice problem number 5. This is 5A, B, and C. So again, it should be really quick here looking at it. Horizontal asymptote, degree on top is 1, degree on the bottom is 1. They are both the same. Yes, I do have a horizontal asymptote. Both degrees are equal to each other. And the horizontal asymptote is y is equal to 2/3. Good. That's the second case. Look at this here. Since degree on top is higher degree on the bottom, we have no horizontal asymptote. It will never go towards a horizontal line where both graphs are going to tend to. Go. And this one. Degree on top is less than degree on the bottom. In that case, we do have a horizontal asymptote, and it is y equals 0. As long as the degree on the bottom is greater than the degree on the top, or the degree on top is less than the degree on the bottom. Yeah, so you really have two choices. Degree on top is bigger than the bottom, degrees are equal, or degree on top is less than the bottom. Therefore, no. So 3 cases there. Okay, and then it gives you a whole procedure of all this here. Do this, do this, do this. to skip all that. Let's go to a problem that we can try together here. So practice problem number 6. And again, I'm going to show each and every single step as you do it. Eventually, you'll get to the point as you see a problem, you're able to factor the denominator by yourself, and you almost at that point you can start graphing it. So at this point, this one right here, you could probably already graph it just by not writing anything down at all. That's kind of where I want to get you. Alright, well, let's go for it step by step. So we have each of the steps. First of all is to factor down into its factored form as much as you can here. So 2x stays, but x squared minus 1 goes and factors down into x plus 1, x minus 1. Alright, and like we said with polynomials, the important stuff is anti-intercepts. Right? Those are very important. And then on top of that, with rational functions, any vertices. I'm sorry, any asymptotes. If you got those, if you got the intercepts and the asymptotes, you're good to go. So let's go for it here. Let's find all the intercepts. Let's find the y-intercept. Alright, and a quick review with polynomials here. How do we find the y-intercept? Yep, set equal to 0. Plug a 0 in for x. See what happens. I get a 0. So my y-intercept is a 0. Alright, what do we do to find the x-intercept? And let's talk about it here, and then I'll erase a little bit here as we go. So, to find the x-intercept, let me do it this way here, and then I'm going to erase it to show you a little something here. That means I do this. Right? In order to solve for x, I would have to multiply both sides by x squared minus 1, right? So I'll do this, but what's x squared minus 1 times 0? Still 0. So technically, I'm always going to multiply by this denominator. So why do that? Why add this extra step? I could just do this here. I could just set the numerator equal to 0 and solve. Cool. Forget the denominator altogether, just whatever is right here. Set it equal to 0, solve. When does that happen? Of course, that happens at 0. So therefore my x-intercept is 0, 0. So the origin is the intercept. Okay, intercept's good. Let's go with vertical asymptote or horizontal asymptote. So any vertical asymptotes here? All yours, what do you guys say? Vertical asymptotes, I have one at -1, I got another one at +1. Alright, next, horizontal asymptote. Perfect, yeah, degree on top is a 1, degree on the bottom is a 2. So, that we got that case, n is less than m, therefore. And just real quick here for students here, don't just put 0 for your horizontal asymptote, because that is actually a line. So you're going to have to always write y equals 0. Same thing for vertical asymptote, you just don't put 1 and -1. You put x is equal to -1, x is equal to +1, because you got your lines happening. Okay, intercepts and asymptotes. If I have that, I'm pretty sure almost all the time I'm ready to go and I can graph this here. So the book also asks you to test for symmetry. And again, do you really need to? More of confirmation you did it correctly. That's about it. So remember with symmetry, all the way to chapter 2, what we do is we plug a -x for x. If it turns out to be the exact same equation we had, we have y-axis symmetry. If it turns out to be an exact opposite of the equation we had, that means means we have symmetry about the origin. Cool. So in this case, and then there's also neither as well. So in this case, because we got the exact opposite, we have symmetry about the origin. So when we make our graph, after we graph it, we'll take a look at it. I was like, yeah, that makes sense for the symmetry. Alright, let's go with it here. So my graph, I got my intercept, which is 0, 0. Let's go with, I have my vertical asymptotes, and it's going to be a little tight here because my graph goes from -10 to 10. If you want to make your graph a little bit more spread out or zoomed in, that's fine too. I get another one at -1. Horizontal asymptote, is that right? Horizontal asymptote is x or y equals 0. Okay, my only little problem, especially at the origin here. Let me give you two scenarios here. And I'll erase it here. It could be that this graph goes to the origin from the top here, coming down, and goes like this. Then it goes like this. And then from here it goes like this. Or it could be that the graph is coming from the bottom this way, comes up, touches the x intercept, comes up like this, and then we have a split direction here, and we also have a split direction here. How do I know we have split direction? Because of the little 1 and 1 right here for my. So we got two different choices here, and this one, I like the fact that it's given already here. I need one more point. If I can just know one more point somewhere along here, then I'll know what my graph is. I need to know maybe like a 2, positive 2. Is it above the x-axis or below the x-axis? Once I know that, I got the rest taken care of. So let's plug in a 2. I just want to see what happens. What happens if we plug in a 2 into our function? 2 times 2 on top, 2 squared minus 1 on the bottom. That becomes a what? A 4. That becomes a 4 minus 1 is a 3. And the graph is a little bit above 1. Once I know that information, I know everything else now. That means this graph has to do this here. Has to come down from my vertical asymptote at x equals 1. It has to touch this point, and then it sort of evens out. And then again, I don't have any more x-intercepts, so then it has to get closer, closer, closer to the x-intercept without touching it. Good there? X equals 1. Split direction or same direction? Because of this guy here, because this little 1 right here, I know we have a split direction, so now it has to come down from the bottom over here. So that means it's going up to touch the 0, 0, and then it keeps on going up again. And this one we know from the polynomials that we learned. Remember, touching or crossing. If it's a 2x, you know it was touching. I'm sorry, you know it's crossing, right? If it was 2x squared, you know it touched and it went back down. So kind of careful there. Okay, then at x equals -1. Split direction or same direction? A split direction. So again, it starts at the bottom, then it turns, never touches the x-axis. Again, there's my graph. It looks like a long process here, but you can pretty much graph this without writing anything down from the previous page, just by looking at the graph, or looking at the equation. Let me just show you one that's actually, and just see if this makes sense here. example problem from the textbook here, just so you see another one before we try it again. So I have x squared plus 2 over, and this is already in factored form, x plus 1, x minus 1. So, looking at the x-intercepts, setting this guy equal to 0. Everybody agreed there's no x-intercepts? There's never a time where x squared plus 1 equals 0. This one actually should have been equal to. Finding the y-intercept, all I gotta do is I plug a 0 in for all the x's. If I plug 0 in for all the x's, I get a y-intercept of negative 1. So no x-intercepts, got a y-intercept or a point coordinate of 0, negative 1. Take the denominator here, set equal to 0. When I get that, these are my vertical asymptotes. I got 2 of them. And real quick here, what is my horizontal asymptote? What's the degree on top? 2. What's the degree on the bottom? 1. If you were to multiply this out, then wouldn't you get an x squared? Technically it would be x squared plus x minus 2, wouldn't it? So you have something looks like this. The x squared goes out. The coefficients are 1 and 1. So I have a horizontal asymptote of negative 1. And then I'll just put this. Okay, good there. Based upon that, do we have enough information to graph this? Well, let's see. X equals negative 2. X equals positive 1. There's my y is equal to 1 horizontal asymptote. And then I know this point here. Well, I actually don't even need these other points here. Because if I know that this point doesn't ever cross the x-intercept, there are no x-intercepts. And I know the point has to touch at 0, negative 1. I know the graph has to be low. Starts low here, comes up to this, touches it, and then comes back down. And then we're talking about split direction right here. And then it sort of slowly starts getting closer and closer to x. Then I know I have split direction here because of the power on the x plus 2 factor. Good there? Which is kind of cool. You can graph it from nowhere. Okay. Give you guys a minute and a half maybe. See if you can go from beginning to end on this one here. to start it as well here. Hopefully you guys are done. So first things first, in factored form, this would be 2x plus 3 and x minus 1. The top does not factor. We good? I mean, there is an x-intercept, but it doesn't factor. And again, once you get to this step, good enough with it here, you should actually even be able to graph it at this point without writing anything else down. But just to write stuff down. Y-intercept, plug it in zeros everywhere. Gives us a y-intercept of 1/3. Everybody okay there? X-intercept, this is the fun one here, setting the numerator equal to 0. At this point, since I just have an x squared, I'm going to solve it for x squared and then take the, should have been a 1 over here. Should have been a 1 over here. And this was going to be a fun one here from algebra. Remember, we can split this off two different pieces, multiply through to get a rationalized denominator. And how about plus or minus root 2 over 2? So again, like I said, the x-intercept probably is the only one you're going to have to really sort of work for to find out what that is. Y-intercept, vertical isotopes, horizontal isotopes, you should be able to see what that is right away. Alright, and vertical isotopes, hopefully you guys got that was already. X equals -3/2 and x is equal to 1. And what did you guys get for the horizontal isotope? Since you have degree 2 on top, degree 2 on the bottom, it is the ratio of your coefficients of your leading terms, which is 2 over 2, which is 1. We good? And again, your book wants to test for symmetry, just to make sure it makes sense. So if you plug in a -x, and the question is this the exact same function, or is it the exact opposite of the same function? Let's see, look at the original one. Numerator is the same, except denominator has a -x, and the original function had a +x. And if you were to factor out a negative out of that, then you get a -2x squared. No, so actually there's neither. It's not symmetric in any which way. I've got a few people doing some corrections here. So at this point, those are my intercepts, is that right? I got a -1/3 for my y. A root 2 over 2. Let's see, root 2 is 1.5 divided by 2 is about 1.7. I'm sorry, 0.7. 1.4 divided by 2, so 0.7 or a -0.7. Vertical isotopes coming down at x equals 1, and then coming down at x equals 3/2, kind of like -3/2. Okay, and then I have a horizontal isotope coming around across as y equals 1. Okay, so again, once you're looking at that, are you able to graph this just by knowing those dots and those isotopes? I think so, yeah. I mean, it's almost like easier to do the inside first right here, this little inside term here. It would have to cross here, touch here, cross back, so that it would have to go like this. There's no other way it can go. And then you're talking about split direction or same direction. There's going to be a split direction on this one. So it has to come down from the top. Gets closer to horizontal, still never touches. On the other side, again, comes down from the top because of the split direction, and done. Okay, another one. Just for you guys to do. This one's going to be a little bit interesting, but I'll let you guys try this. This should be 51, I think. still have time for the exam here. So how about this? You guys try a little ahead of me a little bit here, and then I'll ask the questions so we can finish off. So first of all is y-intercept. I'll wait till someone answers. 1/2 is good. Cool. X-intercept. X-intercept. When does x squared plus 1 equal 0? It doesn't. X squared plus 1 can never equal 0 because if you subtract 1 from both sides and you start taking the square root of both sides, you can't get to the square root of a negative when it's imaginary. Cool. Alright, vertical asymptote. Cool, I'll go with none because x squared plus 2 can never give you a 0 because you get another imaginary. That's weird. Okay, horizontal asymptote. Y equals 1. Cool. Trained you well in that already here. That's cool. Okay, that should be a 1 there. Okay, and symmetry. Plug a negative in for the x. And what do we get? That same exact equation. Perfect. So that means we have an even function in our hands. And we have ourselves y-axis symmetry. Okay, based upon that information, I got a y-intercept of 1/2, no x-intercepts, no vertical asymptotes. I got a horizontal asymptote of 1, and I got symmetry. What does this graph look like? So there's my 1/2, and there's my horizontal asymptote. Well, let's see, my y-intercept is below the horizontal asymptote. And yes, you actually technically could go beyond the horizontal asymptote and come back down usually, but that's going to give a more complicated equation. That was a pretty very simple equation. So the graph goes like this. It starts slightly under the horizontal asymptote, goes down across, sort of dips a little bit here to the 1/2, and then comes back up a little bit here closer to the horizontal asymptote. Is it symmetric about the y-axis? Yeah, sure looks good to me. Again, you'll see some weird ones like that on the homework too. Okay, so one thing we still need to do is not a horizontal asymptote, it's called an oblique asymptote. So think of horizontal asymptotes as a horizontal line. Think of oblique asymptotes as a diagonal line. So it comes across. And so when does this happen? When do oblique asymptotes happen? Interesting. The degrees of nx is greater than the degree of dx, and I forgot to put it in here, by 1. Or said a different way here, oblique asymptotes happen when this is the case, when it's n plus 1 equals m. on top, or maybe we should write it the other way here, sorry. This one. The degree on top is higher than the degree on the bottom by a single degree. So if it's degree on 3 on top, it's degree 2 on the bottom. If it's degree 7 on top, it's degree 6 in the denominator. So how do we calculate these here? These are not too much fun to calculate here. Let's do an example from the textbook first. Then we'll start graphing it. Once we get to the oblique asymptotes, we'll take the extra time to look at that. So again, in your textbooks here, don't really need to write it down as opposed to pay attention here. So for the x-intercept, I'm going to look for x squared minus 4. When does it set equal to 0? It sets equal to 0 when x equals to 2 or negative 2. Plug in a 0 for the x. That becomes 0, that becomes 0, that becomes a negative 4 over 1, or negative 4 for the y-intercept. Alright, do we have a horizontal asymptote? Yeah, x equals negative 1, right? So if I say, do we have vertical asymptote, sorry. Do we have a horizontal asymptote? No, because degree on top is bigger than degree on the bottom. But now the next question after that is, because since we don't have a horizontal asymptote, do we have an oblique asymptote? That's kind of what we're going to get into next. Do it this way here. Okay. The book doesn't actually show you the work involved in getting it, but here's the work involved in getting it. We have to divide that into x squared plus 0x minus 4. We've got to do long division. Hey, that's why you guys practice long division. X times what gives you x squared? X times that is x squared, x times that is x, and we subtract. So that's gone. Looks like 0 subtract 1. Everybody okay there? So then x times what gives you a negative x? Negative 1. Negative 1 times x is negative x. Negative 1 times that gives me a negative 1 as well, right? And we're subtracting. Or we can actually just add the opposite. That's kind of cool too. That's gone, and this is a minus 3. So we've got a remainder of negative 3. And we actually don't care about the remainder. It's this quotient here that we're dealing with. Here is your oblique asymptote. It's y is equal to x minus 1. It's kind of like a horizontal asymptote, but it's a diagonal. That's about it. So let's see how those graphs on the graph here. So there's my horizontal asymptote. X equals negative 1. Look at that. There's my oblique asymptote. It's the line x minus 1. And again, y-intercept, the two x-intercepts. There's only one direction it can go. It's going to get close. It's going to be very close to the vertical asymptote as it starts. Hits the x-intercept, y-intercept, and it goes off very, very close to the oblique asymptote. Alright. Since we're running out of time here, let's do this one here together. So give me y-intercept. This 2 is pretty good by me. X-intercept. Trying to solve for x was not going to work because of that vertical asymptote. Vertical asymptote, x equals 1. And then do we have a horizontal asymptote? N is greater than m? No. Yes, we do. Alright, can you find me that oblique asymptote? So again, have to do long division here. And long division on our hands here. X times x gives you x squared minus 1. So subtract or add the opposite gives you x plus 2. Are we okay with the plus 1 here on top? 1 times x is x, 1 times the negative 1 is minus 1, and then we're going to subtract or add the opposite. We get a 3. That's okay, we don't care about the 3. We care about just the quotients. So I have a oblique asymptote, which is y equals x plus 1. And again, and your book just wants to check symmetry, just in case. Plugging a negative in for the x. And if we do that, we get ourselves that, which even if I factor out a negative on the bottom, and I put it out in front, is that the exact same thing that I started with? No, got a little plus 1 right here that we didn't have before, so there's no way. So we should not find any symmetry here. Alright, based upon that, give you guys a minute here, can you graph it? Alright, here's what I got here. Vertical asymptote x equals 1. I got a y-intercept at negative 2. And an oblique asymptote of x plus 1. So again, based upon that, can you figure out what the graph should look like? Well, let's do some ones that don't make sense. Starting off here, would it make sense that the graph goes this way? If the graph went this way, I would have had an x-intercept here somewhere. I would have had a y-intercept being positive, right? It would have hit there somewhere. Doesn't make sense. Okay, the one that makes sense is that the line was underneath the horizontal, or the oblique asymptote, came across this way, and then it touches the y-intercept and then comes back down. There it is. That makes a whole bunch more sense. Split direction or same direction? At x plus 1. It's a split direction here, so see the graph goes like this. Split direction means the graph goes up like this. It comes down for a little while, but again, it's going to turn right here because of the oblique asymptote here. When it turns, does this, and then does does that make sense for the graph? No x-intercepts, one single y-intercept, and there is no symmetry. Alright, let you guys practice those.